ellipse happens to go through the points 3, 7, and 3, negative 1. I guess you couldn't really check the foci because on an ellipse, are foci on the ellipse? No. So we couldn't check the foci, but we could at least check the vertices. What did you guys see when you were trying to look at the example from yesterday as far as what the equations looked like for the ellipse in parametric form? What did the x have? Had a cosine. And just cosine of t or cosine of theta, right? So you could do the cosine of theta or cosine of t, either way. But what was in front of that cosine? It was a number, and that number ended up being the... Oh, wow, this is really oriented nicely, but that means that I can't go back to what I wanted to go back to. Yeah, right? Oh, Oh, there it was. The 2 ended up being the exact same thing as the minor radius, and then the 3 ended up being the exact same as the major radius. So technically the 3 was the B, no, was the A, and the 2 was the B. But remember, it's just the coefficient that goes along with the term that you're looking at. So the x, that'd be the horizontal radius, and the y, that'd be the vertical radius when you square root the two. So we needed to figure out from the clues that they gave us as to what the major and minor radii were. So then hopefully you guys went to these clues and said, all right, let's figure out what's going on. What did you figure out about the vertices? Yeah, vertical. They were vertically apart. That's a good observation. So we had 3, negative 1, and we also had 1, 2, 3, 4, 5, 6, 7, right? And the vertices, is this the major axis or the minor? Good, because the vertices are on the edge of the major axis. So I know that the ellipse actually kind of does this sort of thing, right? So where would the center be? Good, 3, 3, because we could just take the midpoint or find the halfway distance, because the entire distance would be 8, right? And so what does that mean about my major radius?
4.
Yeah. And what's that going to go with? Is that going to go with the y or with the x?
Y.
Yeah, it is going to be the A, but it's also going to go with the y because it's vertically oriented. So I know that's a 4 right away. Now, what was the struggle about getting the x's coefficient? Technically, it would be the b.
16.
I don't think it is supposed to be 16 because it needs to be smaller.
You have to solve for b.
Solve for b using what formula?
16 minus 4.
Minus b squared. So I know that a that we just talked about is 4. So 4 squared would be 16 minus b squared we got to solve for. And what do we know about c? And how do we know it's 2? Yeah, it's going to be 2 up, right? 2 up from the center and then 2 back from the center, however you count them. So we know that our c is equal to 2. So then we go ahead and plug in 2 squared. So we have 4 minus 16, which would be, Colby, stop hitting people. 2 minus 16, sorry, 4 minus 16 would be negative 12. Divide by a negative, that would just be 12. Square root both sides. It would be square root of 12, which is the same thing as someone already rationalized at 2 root 3. You guys agree? So then that's what we would plug in here. There was a good question that I heard. I heard that they didn't tell us t. It's okay just to go with theta because they're just asking for the path, and this would give us the path. They're not asking for the timing and something that's going faster or slower, making so many laps in it. They're not asking for any of that. They're just saying get us the path. Thomas. I only know it's not centered around the origin because my vertices were displaced. Oh, no, that's a great question. Was that your question too, Colby? Okay. So far, we took just yesterday's example. And yesterday's example said, oh, well, as long as we can have a cosine, have a sine, and we can plug in an A and plug in a B, then we're done and we're good. But that's kind of what I was wanting you guys to check in your graphing calculators. What would happen if you did graph this in your graphing calculator? It'd be around the origin, because what was yesterday's example? Around the origin. We'll struggle. What do we do if we need to move something off the origin? Yeah. y minus k and x minus h, right? So hold on. We weren't wrong, but it wasn't supposed to be set equal to x and y. What was it supposed to be set equal to? So this wouldn't be the finished product, but it is an important step in the process. This will get us our ellipse with our major and minor radii, etc. The only problem is it's not going to be centered in the right place, so it's not going to be that exact path. So what would be my x of my vertex? My y of my vertex? So then if I want my parametric equations, how am I going to finish this off? 3 plus 2 root 3. Open up your notes. Let's go ahead and add this in, just in case it does show up again. The general equations for an ellipse in parametric functions. The general equations for an ellipse using parametric, I should say equations. That'd be the better way of saying it. Using parametric equations. So, this is what we saw yesterday, which was good. This is what we saw yesterday, which is good, except didn't we just see that that's not always going to be the case? So instead, let's make this a little bit more practical. Let's make it a little bit more general. And let's say, okay, if you have x minus h quantity squared all over a squared plus y minus k quantity squared all over b squared. So if we do have an h and a k, which would be in the clue form, we just saw, oh, we'll put that in because it'll be x minus h equals. So we'll go ahead and just move the h to the other side for sake of simplicity, and then a. I mean, Colby, I'm assuming that a goes there, b goes there, but you're right. Depending on who's larger, the a could switch to a different place. So a could be under the y and b could be under the x. But either way, we'll assume for right now a is there, b is there. So h plus whatever the coefficient is underneath the x times cosine of t or cosine of theta. You can put either one. And then y is going to equal k plus b sine of t. Now there are technically special parametric equations for circles. Well, what do you think is going to be different if it's a circle? Good. A and B are just going to be the same thing. All you need is the major and the minor to be exactly equal. Bless you, bless you. So that's not going to be a big difference. That's going to be about the same. So there can be parametric for circles. There can be parametric equations for ellipses. There can be parametric equations for hyperbolas. How would we get that? Hyperbolas. Isn't it just like ellipses but with minuses instead? Throw in a minus. It's not going to work. Oh. Why? Because sadly, cosine squared plus sine squared is always 1. We use a trigonometric identity that has to have a plus. It only goes with ellipses. Can anybody think of, I'm coming to you, Janelle, hold on. Can anybody think of a trig identity that doesn't have a plus, but still would go to 1? It's getting too complicated. Tangent squared plus 1 equals secant squared. Could we rearrange that and have a minus? Ooh, oops, undo. I don't want to totally erase my notes. Tangent squared plus 1 equals secant squared. So couldn't we? Yeah. Couldn't we do the secant squared and then move the tangent squared to be on the same side, and then we would equal 1? Ooh. So then how could we do that? Well, what if we did x is equal to 3 secant of t, and y is equal to 2 tangent of t? Then couldn't we divide by 3 and divide by 2 and square and put together with a minus? That's our hyperbola. So to get a hyperbola, we could also have special parametric equations for hyperbolas. The only struggle is that's not the only property that would work. Couldn't we also do, isn't there another property? Cotangent squared plus 1 is cosecant squared. So we could actually also use cosecant squared. And that would work. So we could have x is equal to, well, technically, With hyperbolas, sometimes x is first and sometimes y is first, depending on the orientation of the hyperbolas. So we could technically even have this one be cotangent of t. So as long as we have secant, tangent, cotangent, cosecant somewhere, that's going to be a hyperbola, all because of the trig. Janelle, sorry, what was your question, kiddo? Yes. Exactly, like as to which one's bigger, which one's smaller. But what's not going to change is that for the x equation, for the y equation, I see some of you being cold, turning up the air. The coefficient that's in the x in the y is the exact same coefficient as the denominator of the x term, y term. Does that make sense? So that makes it a little bit easier, but yeah, you're right. Like if you're memorizing strictly, you have to be aware that that a and that b might not always be in the same place. My paperclip needs to be adjusted, sorry. Now let's try. Uh-oh, now it doesn't go down. Yes, Carl? I don't know if I have tissues. You can grab a napkin if you can find one. Oh, struggle, guys. I'm sorry. But you're always really cold. Okay, let me see if I can get this working. While I get this working, that was the end of section 10.6 notes. You guys are in your notes writing that down, right? So let's go ahead and pause. We're going to grade 10.6 in just a second and see how you guys did and see what questions you have. But since you're already in your notes and the thermostat is not being, well, the thermostat's fine. My paperclip isn't working. Guess I'm not supposed to really be breaking into it anyway, but you guys are cold. Said if you could find them. You've been in this cupboard before. Oh, or the paper towels right there. Go ahead. Come on. Thanks, Jack. I didn't remember they were back there. Why are we making fun of anyone? I think we should be taking notes. You're welcome. Okay. Whew. The air is turned up. Why are we still talking? Let's focus. Ooh, that looks nasty to draw, huh? Ugh. See some spider webs out there. All right, so a couple things real quick before we actually go graphing points. We need to figure out who is r and who is theta. Well, you see circles. Who do you think r is?
Radius.
Hey, go team. You see theta, who has he always been? So I have r being radius. Radius of what? Radius of the circle that you're working with. Theta, he's going to be the angle of rotation. Rotation, we're going to work with or go in standard position, meaning a positive angle is going to start from due east, like standard position of XY graphs. We're going to start due east and rotate counterclockwise like we've always done. If there's a negative angle, I suppose we could go clockwise. That's fine. So we'll do angles, or we'll rotate angles the same way we always have. But radius is weird. If I was to zoom in on the very top of these notes, maybe you guys weren't able to really read what's on this little picture diagram on the right. R is, you can think the radius, but another way of thinking about it, it's the directed distance. Directed sounds like a vector. Direction? That's okay. Directed distance. So here's the idea. R. R denotes how many radii to go out from the origin. The origin is not a circle. The origin is just a point. So the origin has a radius of 0. So if r was ever equal to 0, you're on the origin. Ooh, wait, but that's what the point was called when we had rectangular graphs, when we had like x's and y's. So I wonder if there's something new on polar graphs. Polar ice caps. These days, if you've heard polar, if it didn't have to do with bear, it probably had to do with the ice caps. What are the polar ice caps? Not exactly. They're at the top of the world or the bottom of the world because the poles, North Pole, South Pole, right? Yeah, no. You can go ask Ms. Zuckerman, who has been to the North Pole. Or is it the South Pole? She's been to one of them. Anyway, coming back. Well, she's been there, so that's interesting. Anyway, so coming back. Interesting. So all the people... She went south to Canada. Makes me trust your theory. Anyway, so coming back. So when we're talking about the poles, think about any illustration that's not flat Earth. Any illustration of our Earth, right? It's a sphere. It's actually elliptical a little bit. But if you were to actually, because it's a little bit squished, if you were to look at the top and the bottom, have you ever seen something like this? Latitudes and longitudes? So this little center point is going to be called the pole. You can think of it as the origin, but technically in polar curves, it's actually called the pole. Think North Pole, South Pole. The origin is called the pole. So I'm going to stop calling it the origin and start calling it the pole. We could talk about this guy, the horizontal axis. We could talk about him as the polar axis. Instead of talking about it as the x-axis or the positive x-axis, we're going to talk about him as the polar axis. If you guys think latitudes and longitudes around something like a sphere, maybe this makes a little bit more sense. Here's a question. How do latitudes and longitudes, how does GPS work if we don't live on a sphere? Anyway, so, because you have to be able to go down and around. Anyway, but coming back. With the pole and with the polar axis, now let's start talking about these points. So the radius. The radius is talking about the distance you go out from the pole, which has a radius of 0. The distance you go out from the pole, which will be a radius of 1, a radius of 2, a radius of 3. The circles that you drew were increasing in their radius size based on how you were drawing them. So a radius r equals 1, r equals 2, r equals 3. But here's the problem. R can be both positive and negative. So here's the directed. If r is greater than 0, if r is a positive number, you are going towards, you are traveling towards the angle. You are traveling towards theta. I guess I could put a theta there. I don't have to put an angle. You're traveling towards the angle of the point. If r is negative, you're traveling opposite theta. You're traveling opposite theta. So not that we should do this in life, but here's a silly example. Sometimes if you see someone coming, you're like, oh, hey, and you're excited and you go towards them. Sometimes if you see your mom really mad coming towards you, what do you do instead? Right? So if R is positive, if this is a positive relationship, or if you were in a positive standing in a relationship, you're like, yay, you're going towards. If it's a negative, something negative's going on, you might be like, just kidding. Okay, so that's what's going on here. If R is positive, you're going to go towards the angle being stated. If R is negative, you're going the other direction. So, question, where would the point 0, 0 be if the first number denotes the R, the radius, what circle you're on, and if the second one denotes the angle of rotation? Where's 0, 0? At the pole. All right, so go ahead and graph in the center of your graph, graph A. There's A. At the pole. Where's B? The fifth circle, good. So 1, 2, 3, 4, 5. Now, the pole doesn't count as a circle. That's R equals 0. You have to go out 1, 2, 3, 4, 5, 30. So maybe here's an easier way of thinking about it. Instead of doing 5 and then 30, because 5 would be 1, 2, 3, 4. This circle, which one? 30. I think it's usually easier to turn to the angle first and then go out. So I'm going to turn to 30, be on the 30 line, and say, oh, I'm going towards. So 1, 2, 3, 4, 5. B. If it was -5, not -30, -30 would just go down, right? But -5, you would see the 30 and be like, and go towards 210. You're always going to go towards, think opposite, 180 degrees away. So that's B. We have A done. We have B done. Where's C going to be? On the 90. Good. The pi over 2 line on the 90 line. Now I'm on the 90. Where am I going? 3 towards 90. So 1, 2, 3. And then where's D going to be? Turn to 150, right? Go back to the beginning and say 5. Oh, sweet. Okay. 1, 2, 3, 4, 5. Wait, you're not in a positive standing. So you're not going to be headed towards that 150. Where are you going to be headed? Towards, well, hold on. What's opposite? There's a lot of lines if you're actually doing this right. Where are you going? Towards, add 180, towards 330. So you're actually going backwards. 1, 2, 3, 4, 5. Whenever R is negative, you're not headed towards, you're backing up. Going the opposite direction. And you can always find the opposite direction by, hey, look. So is this the exact same point as positive 5, 330 degrees? Because when positive 5, 330, say go to 330 and go towards 330. And you're like, okay, cool. That's the same point. Here's what's crazy. In an XY graph, there's only one point for every position. In a polar graph, wait a minute, this is totally dependent on angles. What could be another way of expressing this letter B? I just showed you another way of expressing letter D. What's another way of expressing letter B? Yeah, you could do negative 5, 2, 10. What else could you do?
Negative 5, 570.
Yeah, or I was thinking easier just adding 360. You could just do 5, 390. But yeah, Colby's like, you can keep on doing coterminal angles, right? How many points could land on a certain position on a polar graph? Infinitely many. Muy interesante. We might be able to do just a little bit more. But we better grade. So let's go ahead and 10-6 out. Oh, that's the homework. Not 10-6. Yeah, 10-6. That's what we are. Parametric. We're going to graph fast, check fast. Just a couple of you might need to make up just a little bit. I know sophomores, you were out Wednesday. You were going to catch up yesterday. So technically, because we didn't get very far into 10-7, now that we've introduced it, we have an idea. And we can really bust it out on Monday. We'll have no homework to go over. But some of you need to catch up on section 10-6 on Monday. This will be in the video if you guys need it. Number 14, you were supposed to plug into a table and then graph. Check your orientation arrow. Did you figure out this thing was swinging down and up? Then eliminate the parameters, solve for t, plug in. You could have stopped here, x plus 3 quantity squared, or you could have actually solved it out. But either way, there we go. General idea, we got it? Number 28. Plugging in, this one you had to use your unit circle. I mean, you could have done in between values, but that's really disgusting. It would have been nicer just to use unit circle values. And so using unit circle values, well, if you guys just used our trick that you didn't know yet, you're welcome. HK, you could go over 2 and down 6. You could make a horizontal radius of 5 and a vertical radius of 4, and you'd be like, sweet, it's an ellipse. But you wouldn't have known whether the object was going counterclockwise or clockwise unless you plugged in increasing order the parameter. The parameter, parametric, interesting. And if you plugged in, the orientation was counterclockwise. Letter B, you guys would have needed to use our nifty trig trick of getting the cosine totally alone by dividing. Oh, look, it's H and it's A. Squaring. Oh, hey, it's K and it's B. Squaring and then putting all together, it's an ellipse. 44 was like a, sweet, let's plug into a calculator. Oh, guys, look, secant tangent. You should have been able to, could have been able to, in homework last night, figure out hyperbolas without me. But thanks for making me feel good that we discovered it today. Then last but not least, this was a homework problem? Spoiled, rotten. Anyway, it's in your workspace if you need it. Do you guys need me to go back to any of the evens? You weren't able to check it long enough? That was your workspace, that's calculator, and then the rest you were eliminating the parameter and sketching. 10-7, what's the main idea? Oh, we can go back to tangent lines. Polar, sorry, just kidding. Polar. And here's the nice thing about polar. If we are rotating and going out, we're not just going to do like rectangular and just connect with lines all of our graphs. We're actually going to be spinning and twirling and, not literally ourselves, but the pencil. We're going to be rotating as we graph. So we're going to have some pretty cool curvy things that might come out. We're going to have some flowers that come out, some roses. We're going to have some other crazy stuff. But just like parametric, you are going to need your calculator to be in the right mode. And not just the right mode, to also have the right window. So what am I saying? On Monday, what do I need you to bring? Calculator. Because some of you didn't bring it, and on parametric, maybe you got a little bit messed up, but on polar, you can get a lot messed up. Because if one little setting is not proper, come on. If one little setting is not proper, even though something could be really, 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 really cool, it could mess up the graph in many, many ways. Oh, this is going to take forever. Hold on. I needed to change one more thing and I didn't. Aha. Oh, you can't see it, even though it's spazzing out right now. This is really sad. Lo siento. Bring your calculators on Monday. That would have been way cooler if it was zoomed in. E for effort. Bye. Thanks, you guys too. Oh, that didn't work. Mode, radian. Well, there it goes. Bye, guys. Yeah, see, it was going to be cool, and then it didn't work out. E for effort.
No. Thomas, do you remember last year first period in English?
Yeah.
She would give us like, all the answers to the reading comp, and then she'd be like, all right, guys, so what's the answer?
Look at that. First time
I'm
in
okay
like
with that.
first time in forever.
Ooh.
I have a little star by my name.
Go, team.
Dude.
Last year
Oh,
was the stupid
Sude. Poor Sude. He lost it.